question number 4.3. Bereken die snelheid van die staalbal onmiddellik na die botsing. Onmiddellik na die botsing. Let's look at the English version. Calculate the velocity of the steel ball immediately after the collision. Let me have a closer look at this diagram. Just study the diagram for a moment and then we'll see there are certain things which we have to know in order to answer this question. Because it's not as easy as it looks. And I think at some stage I'd like to bring in a new diagram of this one so that we can exactly see what is happening. Or I'll have to use my old one again. Okay, let's go back to the whiteboard. Now you would have noticed that the ball came down, right down. Then to bottom, it has a certain amount of energy. And that energy I call the mechanical energy. Okay, and there the velocity I said to you earlier is at its highest, the largest velocity you can get. And then it hits against the crate, all right. So we have two types of things happening here. One is a swing with mechanical energy, and the other thing that happens here after that, a split second later, is that I have a collision between the ball and the crate. So tussen hierdie staalbal en dan later aan, ek dink as ons kyk na die Afrikaanse een, die staalbal en die, ja, het bots teen 'n stilstaande krat. Dit wil sê, hier is 'n botsing aan die gang. En nou sien ek dat ek het twee gedagtes. Maximum energie en daardie energie word gebruik tydens die botsing. En nou nog 'n weeggeepunt. Hierdie vraag vra 7 punte en baie leerlinge het nie geweet hoe om dit te benader nie. My gedagte is, en dis altyd 'n wenk wat ek gee vir my leerlinge in natskei, is as jy 'n enkele berekening moet doen, dan gaan die eksaminator jou nooit meer as 3 punte gee nie. Het jy gehoor? 'n Enkele berekening. Nou as jy 7 punte gee, kom ek gaan terug na my witbord. As jy 7 punte gee, dan beteken dit eintlik ek moet 'n berekening doen vir 3 punte, nog 'n berekening doen vir 3 punte en dan gee my so 'n ekstra punt eers vir 'n optel of 'n aftrek wat ek moet doen. Dit is altyd die wenk wat ek gee. So nou weet jy moet 2 dinge doen. En wat is daardie 2 dinge? Eerstens, ek dink as ek gaan kyk, ek sal 'n botsing moet doen en die botsing is dan momentum. O, hier begin die dinge nou baie duidelik word vir my. Hier nou is ek in momentum. En hier is ek nog besig met energie en natuurlik meganiese energie. So ek sal eers iets hier moet uitwerk en iets dan sal ek later daar moet terugkom. So onthou dit nou, meganiese energieberekening en dan momentum waar daar 'n botsing natuurlik is. Kom ons kyk weer na die vraag vir die laaste keer en dan gaan ons hom probeer aanpak. Die Afrikaans. Die vraag sê, bereken die snelheid van die staalbal onmiddellik na die botsing. Nou gaan ek 'n lyntjie trek op my blaai en sê, goed, as die eksaminator vir my, ek moet 2 berekeninge doen, dan gaan ek 2 berekeninge doen. Hulle vra vir my, bereken die snelheid van die staalbal. Wat het gebeur? Die staalbal en die krat het gebots. So hy het ingekom met 'n sekere snelheid en ek ken sy massa al. En hy het stil gestaan met 'n massa en 'n snelheid van 0. Daarna vir die botsing plaas en na die botsing toe beweeg, ja, toe beweeg die krat daardie kant toe en die bal het ook natuurlik beweeg en miskien nog weer teruggeswaai. So hy het ook toe 'n eindsnelheid gehad. En daar was sy beginsnelheid. En hy het 'n massa en hierdie een het sy eie massa en ek dink sy massa was 0,1 en hierdie een het ook 'n eindsnelheid gehad. Ek dink hulle sê vir ons wat sy eindsnelheid is. Ja, die botsing van die krat, sy eindsnelheid was 3,5 meters. Goed, nou het ek 'n sketsing geteken wat aan die einde gebeur en wat wil die eksaminator weet? Hy wil hierdie snelheid hê van die bal. As ek seker maak, bereken die snelheid van die staalbal onmiddellik na die botsing. So dis voor die botsing, dis na die botsing. Hier kan ek sien gou-gou dat hierdie een se momentum, want dis momentum is die produk van massa en snelheid. The momentum here was 0. I can see it because any mass times 0 will give me 0. And the momentum of this one would be, what is the mass again? 0,5, that's the ball. And the velocity, oh no, I don't know the velocity. So that means I need to know that velocity. And then I can move to the right hand side and I would have to find that velocity. Okay, so that means my mass would be 0,5. I would have to find the velocity and here it would be, if I add the momentum there of that one, it would be 0,1 and I multiply that by 3,5. So there I have a slight momentum question. But now I have a problem here. How do I get the velocity of the ball? But where's this ball coming from? Of course, the ball was swinging from the side. Swinging from the side. And while the ball is swinging, what kind of energy? Kinetic energy. And what other kind of energy does it have? Potential energy. Okay, I'm on my way. So let's see what we can do about this one. Okay, first of all, I'm now working with those two kinds of energies. So on this side, I'm going to do my calculation 1. On that side, my calculation 2. Let's do this one first. I now do and say I need to know the mechanical energy. But wait a minute. The mechanical energy at point C must be the same as mechanical energy at point B, because that is what the law of conservation of mechanical energy is saying, that mechanical energy at any point between A, B, and C must be exactly the same. So, how shall I write it down? I will then say that the mechanical energy, that is U plus K, at B, that is that point there, must be the same as that one there, must be equal to the mechanical energy at C. Het julle hom? Die meganiese energie langs enige pad, van enige hoogte, sal altyd dieselfde bly. Dit wil sê, potentiële energie plus kinetiese energie sal altyd dieselfde wees. Hoe by B sal dieselfde wees by C, is gelyk aan daardie by A ook. So, what do I know? But I've calculated this before, this one. Let me just see. Yes. Here we go. So that's 5,19. And that is equal to, and now I've got to do some calculation here. This one is mgh, and that was half mv squared. So that one is mgh, and the other one is half mv squared. And I know the mass by now. The mass of this one was 0,5, but wait a minute. I'm now at the bottom. That means h is 0. H is 0, and therefore the total thing is 0. So that's 0. plus half, and that m was 0,5. Oh, I get it now. I can get v, and that is times v squared, the final velocity when it comes to the bottom. And after, let me see what's that now quickly, which means that if I want v f squared, I've got to take the other side, 5,19, and divided by a half, which is 0,5, and another half, which is 0,5. Let me take my calculator and you do the same and see if you get the same answer. So it's 5.9, that we go, and I divide it by 0.5 times 0.5, close my bracket, and I divided that, did I? No, I added, oh, and I divided, that's correct. And that's 23,6, which is 23,6, but I need to get rid of this square because I want that one. Almal saam met my en ek kry die vierkantswortel daarvan. Square root of 23,6. En 'n verrassende antwoord 4,85. I have in this case 4,85 meters per second. So, what did I do here? I was trying to get my final velocity by using the law that they asked me in the first place, the law of the conservation of mechanical energy. So that is what I was doing. Simply applying the law of mechanical energy, conservation of mechanical energy, meaning that the total mechanical energy in any system is constant. At any point, mechanical energy would be the same as at any other point. Okay, so they have an answer, and where am I going to use that answer? Oh, that answer I'm going to take right up there, because that is what I need in this case. Okay, so I'm going to allow you to try and do it yourself. I'll do it slowly for you so that you do not have any problems in understanding what we're doing. So it's 0,5, multiply that by 4,85, plus 0 is 0, and that is equal to, because we always say that the total momentum before is equal to the total momentum afterwards. So I could write this here at the top. The sum of the momentum before or initial is equal to the sum of the momentum final. Therefore, the momentum is mass times velocity plus nothing is equal to the sum of the two momenta. So it's this one, 0,5 Vf plus this one here was, the mass was 0,1. I'm sure the mass of the crate was 0, that's right, 0,1 times that. So I'll do that very quickly. I'm just getting like the learners. Ek kan nie sonder hierdie sakrekenaartjie klaarkom nie. 3.5 0,35. What do? I want to maintain that one, which means I have to take the other one across. Now let me do this one quickly. 0.5 times 4.85. Okay, and that is equal to, and then I subtract that one because I'm taking it across, minus 0.35, and this is what I get. 0,5 Vf is equal to 2,075. Okay, and now to get the final answer, because I want the final velocity, I simply take that one across, 0,75 over 0,5. Okay, let's just see that. If I now do that, I divide it by 0.5, I get 4,1. 4,15 meters per second. Okay, I'm not going to say a lot of things. I think you got the idea, but let me just summarize for you by using a green cokie and go over some important aspects. Let me just summarize it on a clean sheet rather for you, and perhaps then you will see what we've been trying to do in this last sum. It was worth 7 marks, but it's worthwhile trying if you know what you're doing. Let's look at the white screen again to see what we've been doing. The crate was there. The ball came down, the steel ball, and this steel ball had some energy. And that energy, you know by now, is mechanical energy. Then, interesting thing happened. A collision happened here between the ball and that took us into the realm of momentum. Therefore, it means, in this case, we were still in applying the law of mechanical energy. Okay, so what did I do? Just to summarize the chief ideas for you in this one, I divide my sum into 2 parts. You, of course, in your examination, you can do it one below the other, but I was using the law or the principle of the conservation of mechanical energy, die beginsel van die bewaring van mechanische energie. En dit lê dat die energie by punt B is dieselfde of is constant soos die energie by punt C. En wat die energie was daardie gewees? Natuurlijk, het was I plus K, mechanische energie. En wat die energie praat ons hiervan, is gelijk die totale energie, bly dieselfde, bly constant by enige punt. En dit was die beginsel wat ons gebruik het. En daarna natuurlijk het ons geweet hoeveel energie ons hierdie kant het, en ons het uiteindelik vir VF van die bal bepaal. Toe gaan ons oor na momentum. En die momentum som sê, die som van die momente aan die begin is gelijk aan die som van die momente aan die einde. Or na die botsing. Dus voor die botsing, na die botsing. Initially, before the collision, finally after the collision. And then of course I added the 2 momenta. It was the momentum of the ball, right, at the beginning, and the momentum of the crate, by the way, which is m times v and m times v. I add those 2, and I make that equal to the momentum afterwards, which again is mv plus mv. And I was asked then, in the last instance, to find this one. And that's what we've done. It was just a summary for you to see what we've done. But please watch out for a sum like this, because sometimes we don't know when to use momentum and when to use mechanical energy. The clue was here. When the collision happened, then I was in the area of momentum. Het julle dit? Voor dit, terwijl die bal nog afgeswaai het en nog nie geraak het nie, was ek in die area van mechanische energie. Ek hoop dat het gehelp.